Number 5, letter A. If half of the weight of a small 1 × 10⁻³ kilogram utility truck is supported by its 2 drive wheels, what is the magnitude of the maximum acceleration it can achieve on dry concrete? And letter B, will a metal cabinet lying on the wooden bed of the truck slip if it accelerates at this rate? All right, so here's a quick picture, right? We have a truck in black, and then in red here, we have the metal cabinet lying in the truck. All right, so what I want to do first is I just want to, just because I'm thinking forward to how to answer letter B as well, what I'm going to do here is I'm going to realize that the total weight, or I should say the total mass, right, of this whole system should be equal to the mass of the empty truck plus the mass of the cabinet, right? Now, it's a little unclear if this value up here at the top, the 1 × 10⁻³ kilograms, if that mass represents the mass of just the empty truck or the mass with the metal cabinet. So fortunately, we actually don't need it as we think through the problem, but I'm just going to detail that out over here, that the total mass of the truck should be simply the mass of the empty truck plus the mass of the metal cabinet. All right. So now it says that the weight, right, of this vehicle is half of it is being supported by the 2 drive wheels. So let's just assume this truck is rear wheel drive, and there are 2 drive wheels back here. One lies, on the exactly behind the other, but I'm terrible at drawing, so I just showed one. All right, but know that there are 2 wheels here. So what we have to think about is we have to think about all of the forces acting on this particular wheel, all right, in order to try to gain insight about how this truck is going to accelerate. So let's draw a free body diagram that details some of those forces. All right, so first there's a weight component, right, on the wheel, right? So the weight is going to be pointing straight down. Now that weight has a value of what? Well, the weight has a value of half of the total weight of the truck. Is that correct? So, in other words, it would be half mg. Okay, and the mass here, let me detail it, it would be m sub t, right, for the total mass, right? Because the weight that's bearing down on these 2 drive wheels are going to be a function of both the mass of the empty truck plus the mass of the cabinet. All right, so that takes care of that. Now, there's a normal force, right, that is also being applied on the wheel directly up. Now, in terms of the wheel, like what part am I talking about specifically? I'm talking about specifically, the part right here where the wheel makes contact with the ground. So this point right here that I just drew will represent this particular point right where the wheel touches the ground. I mean, right now the truck is levitating, but I think you get that, right? So the wheel should be touching the ground there. All right. So there is a force that the ground is pushing back on the truck, meaning on the wheel here, right? That would be called the normal force, and that force is pointing now straight up, and it's equal in magnitude but opposite of the weight. So therefore, the normal force here is going to be half mtg. Okay, great. Now let's talk about what are some other forces. Now remember, I'm going to assume the car is going to want to move forward. Okay, so it's going to accelerate in this particular direction to the right, and there's going to be some applied force pushing it to the right. But I have to think about how the forces on the wheel and the road are acting on one another in order for me to determine, the forces acting on the truck as a whole. All right, so let me do this. Let me just quickly, I'm going to draw a new picture. Here's the road, and here's the tire. Okay, so now, if the truck were to move, like we said, to the right, how would the wheel have to rotate? Well, it would have to rotate in a clockwise fashion, right? If the wheel rotates here in a clockwise fashion, it will propel the truck to the right. Well, how does that actually happen? Well, this is how it happens. So as the wheel rotates to the right, the wheel, right, is essentially pushing the ground backwards, right? So right here, if I were to draw a little vector here, right at the point where the wheel makes contact with the ground, This is the force that the wheel is applying to the road, correct? Now that's great, okay. But remember Newton's third law, that there should be an equal but opposite force here, especially if there is an equilibrium between the two, okay? And I'm assuming that there's no slippage here, right? That the wheel is gripping the road perfectly. So, in order for that to happen, there must be then an equal but opposite force pointing the other way. Now, what is that force actually called at this point? Well, what force opposes the motion? Remember, the wheel wants to rotate this way, and it's rotating, at this exact point, it's rotating or pushing to the left. So the force that opposes that is called the frictional force, right? Now that frictional force should be exactly opposite of the applied force. Now, it's the static frictional force, again, because that'll give us the maximum acceleration. We don't want the tires to spin, right? If anybody has done burnouts with cars, obviously you know this. So, you don't really need to even do burnouts in order to know it, but I think it should make some sense. So, it's actually this force that is going to be propelling the car forward. Okay, remember, I'm interested in detailing the forces on the tire, not produced by the tire. So this force is produced by the tire. But the force of static friction is the force applied to the tire by the road. So that's the one I'm going to detail in my picture here, because that's the force that's going to be pushing the car forward. This is the force of static friction. And that is, ladies and gentlemen, why this car will move to the right. All right, so now you can see how these vectors line up. All right, great. So now what I realize that this force of static friction is the same as the force pushing the truck forward, which will then allow me to realize that force equals ma. That should allow me to calculate A, right? Okay, so now let's detail the force of static friction here. All right, we have a formula over here on the right-hand side. I'm going to use that, okay? So we have the force, right, of static friction is less than or equal to the coefficient of static friction multiplied by the normal force. Now, in this particular problem, right, for this tire right here, the force of static friction should be less than or equal to the coefficient of the truck, right? Let me not say the coefficient of the truck. It's the coefficient of static friction between the truck's rubber wheels and the dry concrete, correct? So I'll just call that mu sub t for the truck, all right, knowing that we're talking about rubber and dry concrete. And then the normal force here, we already found that before, that was this value over here. So let's plug that in. So that's half total mass times gravity. Okay, so now we should be cool so far. Now we have the realization that I described before. The force of static friction in the problem is equal to the, I'll call it the force of motion, or the force, I'll call this little m down here, right over here I just drew. Okay, this little m. That's the force of motion. We just discussed that. So now I realize that the sum of the forces then in the x direction should equal the mass that is being accelerated multiplied by the acceleration of that object in that direction. So remember, this is the force of motion, and it is being produced by the force of static friction. And we know the force of static friction is this. Now you might say, well, wait a minute, it's not equal to, it's less than or equal to. Well, remember, we're trying to find the max, okay, maximum acceleration. And therefore, I'm going to take, it says less than or equal to, so I'm going to take the equal to, all right, variety. So now what I'm going to do is substitute this into this equation for force. Let's do that. So we have the coefficient between the truck, the rubber tires, and the road, multiplied by 1/2 the total mass times gravity, right? That should now equal this side. So what's the mass of the thing that is being accelerated? Well, this whole thing is being accelerated, so that's the total mass, correct? Meaning including the empty truck and the cabinet. And that's multiplied by AX. Now here's the interesting thing. What can you cancel here? These go bye-bye, right? And if they go bye-bye, what are you left with? And I'm just going to rearrange this side now. All right, so you're left with 1/2 the coefficient, right, between the truck, meaning the rubber, and the dry concrete, times gravity will equal the acceleration now of the truck. Oh, cool. Okay. I'm going to box this because we're going to come back to it in a second. All right. But this is now how we get our answer. So in order to answer the question here, it'd just be simply 1/2 times, we got to go to our table now, find rubber on dry concrete. There it is. And the coefficient of static friction is 1. So we plug that in, 1.0. And then gravity is 9.8, right? Multiplied by A sub x. And look, this works out to be 4.9, right? 4.90, whatever, meters per second squared is equal to the acceleration. So that's how we get our answer. That's how we get our answer to letter A. That was a combination of letter and answer. All right, so that's A. Okay, now let's take a look at part B. So let's detail it here now. All right, so again, I'm going to try to be very general. I'm going to work through formulas in this problem because it'll make it a lot clearer. So here, assume that this now is the bed of the truck, not the road anymore. I'll write that. This is the bed of the truck. And we have this cabinet now lying on it. Okay? And let's see. Hold on one second. Okay, so this cabinet has a certain mass, right? We called it before. We said that it has some mass. I don't know what it is, but it has a mass to it, and I'm labeled that M sub C. Now, this also has a coefficient, right, of static friction between these two surfaces, right? Remember, letter B, I'm trying to figure out if this metal cabinet, which lies on a wooden bed, if it will slip or not. So once you hear the term slip and whatnot, you're thinking, well, did I overcome the force of static friction or not? Okay, because that is the point at which it will slip. Now, I know that there is some friction going on between these two surfaces. So in that case, I need to now detail a free body diagram at this particular point. So let me do that again, but for the cabinet. So I'll draw it over here. Now there's a certain weight, right? The cabinet is pushing down on the truck bed. So let's detail that here. So there's a certain weight. And how would we represent that weight? Well, we'd say it's equal to mg, but we're just going to say mc sub g because that would be the mass of the cabinet. Now remember, there's no accelerations in the y direction, therefore the normal force here is also the same, but opposite in direction. Okay, that we spoke about a little bit before. So the normal force here will be m sub c times g. Great. And now when we think about the frictional forces, right? Now remember, there's going to be we don't want it to slip, okay? So there has to be some force propelling it forward, and it's going to be the exact same. I'm just going to try to breeze through this part, but it's going to be the exact same reasoning as we used over here, all right? If you were to think about what's going on in this particular picture. So just know that we have the same basic setup here, that the force here of friction is pointing to the right, and that's what's going to be pushing it to the right. Okay, there's the force of static friction, but now it's not the same as this, all right? It's the same concept, but not the same number, because here I am talking about, right, the cabinet, not the entire truck. Wow, I apologize. I think a 747 might have just landed on my driveway. Hold on. Oh, no, it's just the landscapers across the street. So, sorry for the noise, but we will persist. And so, we have the force of static friction here being the static friction between the cabinet and the bed, right? So we can detail that formula. That hasn't changed. The nature of the formula hasn't changed. So the force of static friction, right, should be less than or equal to the coefficient of static friction multiplied by the normal force. So now let's start thinking. So the force of static friction in this part of the problem should be less than or equal to the coefficient of static friction. I'll call it the coefficient of static friction between the cabinet, right, and the bed, so metal and wood, times the normal force. And remember, we found that the normal force here should be mc times g. mc times g. Okay, great. All right, so now, what do you think? Well, I know where we're going, but I was going to ask you a question. Where do you think we're going? But then I realized that you can't answer me. Oh, well, you could answer me, but I just won't hear. Think about where we're going to go next, right? We're really in the same spot as we were over here. All right, so we have to realize that, again, the force of static friction here is going to be equal to the force of motion propelling the cabinet forward. Okay, so what that means is that we get down to this formula, right? Some of the forces in the x direction should be equal to the mass of the object that is accelerating multiplied by the acceleration of that object. So we have basically what we're going to be doing again is we're going to be substituting this now into our force equation. Okay, so we have the coefficient for the cabinet times the mass of the cabinet times gravity should equal now the mass of what? Well, what are we talking about accelerating? Well, you might say, well, we're talking about the truck accelerating, but yes, I mean, we're trying to compare the two, but we're talking about this system specifically, right? The cabinet on the bed. So we're really concerned about that particular mass multiplied by its acceleration. So notice what's also interesting here. What happens to the mass of the cabinet? Bye-bye. It goes by. Goes bye-bye. So we realize now we have that the coefficient of friction between the cabinet and the bed times gravity will equal AX again. Now I'll box this. Okay. Well, I tried to box it, but it turned into a circle. Well, not a circle, an oval. So now what we need to do here is now we have to say, well, it's asking us, will it slip? So really what I want to see is what happens when the accelerations are the same, because the accelerations are the same, right? If it doesn't slip, then that means the accelerations will be the same, right? So what I'm trying to detail now is I'm saying that the acceleration of the truck must equal the acceleration of the cabinet, okay? So what formula did we come up for with the truck before? We came up with this one. Well, actually, no, sorry, this one, I boxed it. So let's take that formula and plug it in. So we have half, right? The coefficient of the coefficient, of static friction between the rubber and the dry concrete times G should equal now the coefficient, right, of static friction between the wooden bed and the metal cabinet, all right, times G. So what else happens here? Well, the G's cancel. Okay, interesting. So what am I now left with? Well, what I'm left with here is it says 1/2 times the coefficient between the truck, right, the rubber and the road, has to be equal to the cabinet between the metal cabinet and the wooden bed. So now, I'll box this. Do me a favor. Go look up at the table above and find where it says metal on wood. Here it is. What is its value? 1/2. Interesting, right? So what is this basically telling us? Well, this is basically telling us that what we already know, right? It's basically telling us that the coefficient of the coefficient between the rubber and the road, all right, should be equal to, well, multiplied by 1/2, that is, right here, right? Should be equal to the coefficient between the cabinet, the metal cabinet, and the wooden bed. So, in other words, what I'm trying to say is that when the accelerations are equal, okay, the coefficients of friction must also follow this relationship. And if they do, then that means that these are also equal, right? So let's see what the numbers actually work out to be. So we have 1/2 times the coefficient, right, for the tires in the road, which was 1, okay, which was 1, equals the coefficient of friction between the metal cabinet and the wooden bed, which was 0.5. Now, is this a true statement? Yes, right? This works out to 1/2, and this is 1/2. So what that means is that they will both experience the same exact accelerations. Okay? So, will a metal cabinet lying on the wooden bed of the truck slip if it accelerates at this rate? The answer would be no. It doesn't slip. It grips it just perfectly. Okay? So it grips it just perfectly. So the answer here is no. It won't slip. Okay? Not at all. So now, let's see. Okay, so that takes care of that. All right? So now, let's see for letter C, it says solve both problems. Oh, fun. Assuming the truck has four-wheel drive. All right, so let's just try to do this quickly because we have all the formulas already, so we can see what happens, okay? So now if the truck has four-wheel drive, what changes? Well, let's go back to the beginning. Guess what changes now? Well, the weight, right? Remember, now the weight, the total weight of the truck now is, or how should I frame this? The frictional forces now are being experienced on all four tires. So therefore, the total weight of the truck now, right, is really producing the normal forces necessary to create frictional forces. So this half gets knocked out, okay, because now it's the total mass of the truck, not half of it. And that means this half gets knocked out. Okay, let's follow it on through. Everything else is the same. That means, actually, you know what, instead of crossing it out, what I'll do is I'll just highlight it in red, okay? So this half gets knocked out, 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 and that half gets knocked out. Right? Okay. So now let's continue on to part B. Everything for part B is identical. Nothing for part B has changed whatsoever. Okay? Doesn't matter if the car had one-wheel drive, two-wheel, four-wheel, 18-wheel, doesn't matter. All right? So let's jump to this part, right, where the accelerations have to be equal, and guess what gets canceled now? This part. The half is not there anymore, right? That means the half isn't here anymore. Is that correct? And what does that tell us now? That tells us now that this has to be the case in order for no slippage to occur. And is this the case? Meaning, are the coefficients in both sets equal? Well, no. One is 1 and the other is a half. So if that's not true, then that means that the accelerations of each are not the same. And therefore, if they are not the same, that means that when I solve then, part B the second time, the answer will now be yes. It does slip this time. And, by the way, I didn't, finish part A. I should have. But if we follow part A, remember the half is canceled here. And what happens now when I do this multiplication? It's just 9.8 now, right? So the acceleration has doubled. All right, guys. So that should take care of it. Thank you so much for tuning in. I really do hope this helped. Please remember to subscribe and I look forward to helping you in the next problem. Take care now.